Related rates. We're going to spend a little more time on related rates. It's the application to everything that you learned so far. Finally, we're going to see calculus in motion and how it's calculus used in different situations. So here's example one. A circular pool of water is expanding at the rate of 16 pi inches squared per second. At what rate is this radius expanding when the radius is 4 inches? All right, so the first thing is we need to figure out what is the question asking us. At what rate is the radius expanding? So that means we want the RDT. Okay, so the first thing we do is usually gather the information, see what we know. Well, first of all, dRdt, okay, that's what we're looking for when radius is at 4. That's what's given to us. We also know the area is changing or expanding at 16 pi. So that's dIdt. All right, so now if you look at this, okay, the hardest question about related rate is how do I come up with the equation that would I need to take the derivative of. So you have to think that okay, it's given area and it's given some kind of information about radius of a circle. So you definitely want to say, well, what equation would involve a and r in a circle, where it would be what a equal to pi r squared. So once you have the equation, we're going to take the derivative, implicit differentiation of this equation. So dA dt must equal to, now we're going to remember, now pi is not a variable. It's just a number, right? Okay, it's a constant. So really just taking the derivative of r squared, which is 2r. So we have 2 pi r, okay, and then times the derivative of r, which is dr dt. Now notice we know what the dt is they provided for us. We know radius is 4, so we're solving for dr dt, and that's exactly what we want. So our dr dt will equal to 2. So to answer the question is, the radius is expanding at a rate of 2 inch per second when radius is 4 at this circular pool. Let's try another one. Okay, example 2. Here's the question. A 25-foot long ladder is leaning against the wall and is sliding towards the floor. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? All right, so something like this sometimes requires some kind of visual here. So imagine we have a wall right here. Here's our ladder that's leaning against the wall. That's at 25 feet. So the top of the ladder is sliding down while the base of the ladder is sliding outwards. Okay, so well, what do we know now? When you see a picture like this, okay, by experience, hopefully you see that look, it's Pythagorean theorem: x squared, y squared, 25 squared, right? So here's my equation. That's the equation we're going to be taking derivative of. Okay, implicit differentiation, that is. Now, what's given to you? So we know that dt, it says in a problem, the base of the ladder is sliding outwards, right, at 15 feet per second. So that's dx dt. Now they want to know how fast is the ladder coming down on the wall, so that's dy dt. And they give you a number. They say when the top of the ladder is 7 feet above the ground, so y equal to 7. So all right, so let's take the derivative. So when you take the derivative of this equation here, differentiation, differentiation. So this become 2x of dx dt. This become 2y of dy dt. And remember, derivative of the constant equal to 0. Now let's plug like previous question. Let's plug in what we know. So we know we don't know x actually. Okay, so what they didn't give us is 24. They did say dx dt is 15. It's right here, right? Dx dt is 15. And they want to know what happened at that specific moment when y equal to 7. All right. So, and then remember, you're looking for dy dt. So you're missing one variable, x here. But what we can do is apply Pythagorean theorem again. So if we don't know what x is, we don't know what x is. But we know we want to know how fast is the ladder sliding down when the ladder is 7 feet above the ground. So y is 7. And the ladder doesn't change. That's 25. So if you solve this Pythagorean, this triangle here using Pythagorean theorem, x will equal to 24. Then we take the 24, plug it in here. Once we have that, we have all the information we need to solve dy dt. So when we solve for dy dt, it's going to be equal to negative 51.42. Now, why is the negative? That's a very important significance when it comes to related rates. Related rates, positive and negative, make a big difference. Because now, if you think about this right here, this ladder right here, if the ladder is sliding downwards, isn't the y is getting smaller and smaller? That's why the change in y is negative, right? The distance, not the distance on the y as this ladder sliding outwards, the distance between them is going to get smaller and smaller. While x is opposite, this as the base of the ladder sliding outwards, x is going to increase. That's why the changing in x, which is dx dt, is a positive, but changing in y is negative because the ladder is coming down towards the ground. So the answer is 51 feet per second. All right, here's another example. A spherical balloon is expanding at a rate of 60 pi inch cube per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? So, all right, so we're talking about volume now this time, right? Inches cube. So dV dt is 60 pi. That's what's given. We want to know how fast is the surface of the balloon expanding. So that's ds dt. That's question mark. And when r equal to 4, we got everything we need. Now we just need what? We need an equation that with surface area in it, not the volume, because remember you want to find ds dt, so we need something with surface area in it. So we know that surface area is 4 pi r squared. Okay, so now ignore the volume for a minute. Okay, so this is what you should be focusing right here, surface area. So when you take the first step, when you take the derivative of this, that's ds dt. Good, that's what we want. And the derivative of the right hand side is a pi r dr dt. Now if you look, we have r is 4, but we don't have dr dt. They never told you that in a problem how fast this radius is changing in respect to time. And that's when we go, all right, since we are giving volume, but that's nothing to do with volume. We need dr dt, right? We don't need dv dt. So that's when we go, okay, maybe we need help with another equation. So another equation will be, well, let's see, we know the volume is 4/3 pi r cubed. So if you take the implicit differentiation of this equation here, dv dt equal to, now which basically this is all constant, so we're taking the derivative of the r cubed. So when you multiply this to the front, 3 and 3 cancel out, so we get 4 pi r squared dr dt. Now the problem did tell you what dv dt is. They tell us that's 60 pi, and you have the 4 pi. Now r is 4, and guess what? From this new information given to us, we can solve for dr dt. But once we find the dr dt equal to 15/16, we can continue going back to what our mission was. Our goal was to find ds dt. It had nothing to do with this dv dt business. But we only did that is because we need to find dr dt in order to proceed and continue finishing our problem. So now we know dr dt is equal to 15/16. All you have to do is just multiply this out, then you get our answer. So ds dt is 30 pi inches squared per second. Okay, so we're gonna do the same question again, but take a look. What's the difference? So if you look at this question, it says a circle is increasing in the area at the rate of, right. So this one is the area one. So we're going back again. Okay, but how fast is radius changing? This time they want to find the RDT. So this is just a review question. Okay, if you take a look, we know ddt is 16 pi. drdt we don't know. We want r equal to 2. So if you use a equal to pi r squared, let's do this one more time. Okay, so derivative of a is dA dt, then this derivative of pi r squared is 2 pi r dr dt. We're looking for dr dt, you know the r, you know dA dt, then simply solve for it. So the rate of change in the radius is expanding at 4 inches per second. Okay, now let's try something different. So you have a rocket that's rising vertically at a rate of 5,400 miles per hour. An observer on the ground is standing 20 miles from the rocket's launching point. How fast in radius per second? Be careful, this is radius per second versus this hours. Okay, so different units. We need to change that. We need to address that when we get there. So it's the angle of elevation. So how fast is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is at an elevation of 40 miles? Oh, let's take a look. So let's look at, oops, hold on. Let's look at the picture real quick. So here's a picture, right? Okay, so you have a rocket is going upwards. You have someone looking at it and it tilting the head looking at it. That's called the angle of elevation. So theta is how fast he's raising his head basically, right? What angle, right? How fast is the angle changing? Now this is the height of the rocket. Okay, so what's given to us DHDT is 5400, but remember the question they wanted in seconds, so we're gonna change that to second. Okay, so it's 3.5 seconds. That's how fast the height of a rocket is changing. Okay, 3.5 second per what is it per second? Okay, and miles. Okay, that's how fast it's going. 3.5 miles per second. Okay. Now, we want to know d theta dt. We know h equal to 40. So this particular question, now it's not like we're using Pythagorean theorem because it doesn't have all three sides, and plus you're not looking for side, you're looking for missing angle. In that case, we need to use trig relations. So tangent of theta. Why do we use tangent? Because tangent is what opposite over adjacent, and that's what was given to us. We don't care for hypotenuse, there's nothing there. So h over 20. So that's the equation we're going to be taking derivative of. So when we take the derivative of this, right, okay, then you get secant squared theta, because tangent becomes secant squared, d theta dt, and equal to 120 dh dt. We have dh dt, but we don't know what secant squared theta is. So this is where you go, all right, you might need to go back and review your trig identity, which I did put it on the canvas on the very top for you. So one of the trig identity for this function is 1 plus tangent square equal to secant square. So if you manipulate this equation, since we know tangent is equal to 40 over 20, then tangent theta equal to 2. So we will plug it back in. We find out the secant square is equal to 5. So we kind of have to do this on the side here. Then now we know this is 5. Well, once we know this is 5, d theta dt is not that far hard to find. We just need to use some algebra. So we can conclude that d theta dt is 3 over 200 radian per second. Okay. Now, our last question here, okay, dealing with a car and a truck approaching an intersection. Okay, the car is traveling at a 60 mile per hour and is zero point 0.8 miles away from the intersection, while the truck is traveling at a slower rate at 30 miles per hour and is zero point 0.6 miles away from the intersection. How fast is the distance between them change at that point? All right, so if you look, here's a picture, right? So you have a truck going towards intersection, so is a car going towards this intersection. Now the distance between them is keep changing, right? Okay, so if you look at this picture here, that's definitely Pythagorean theorem. So we're gonna let s be the distance between them, and x be the truck, and y be the car. So, and then what we know is, now be careful. Even though it says the car is approaching at 60 mile per hour, but it didn't say what direction. If you think about it, the car approaching, so that means what, y is getting smaller and smaller. That's why dy dt is negative 60. That you need to figure it out. Even though it didn't say negative, but it's implied that dy dt should be negative. And then dx dt will be negative as well, right? Negative 30, and then you have all these numbers. So you use the Pythagorean theorem, x squared plus y squared equal to s squared. Then when we take the derivative, you have 2x dx dt plus 2y dy dt equal to 2s ds dt. Plug in everything we know. Now the only thing you find out is s is missing. But again, we can use Pythagorean theorem. If this is 0.8, this is 0.6 away from the intersection, s must be what? Equal to 1 using Pythagorean theorem. Coming back, plugging 1 into the equation that we just find with implicit differentiation, we find out that that ds dt will equal to negative 66, which is true because this distance getting smaller and smaller approaching to the intersection. So there will be closing in at 66 mile per hour. That's how fast this s, the distance between them, changes.